Welcome students. Today we are going to study infrared spectroscopy. Infrared spectroscopy is very useful in the identification of an organic compound. The identity of an organic compound can be established from its fingerprint region. This technique helps to establish the structure of an unknown compound. The presence or the absence of absorption bands helps in predicting the presence of certain functional groups in the compound. IR spectroscopy technique is quite useful for studying chemical reactions. IR spectroscopy is also useful in the detection of impurity in a compound by comparing its spectrum with the spectrum of the authentic sample of the compound. A pure sample always consists of sharp peaks and bends, while impure sample will consist of poor bends and also some additional bends. Region between the visible and microwave of an electromagnetic spectrum is called infrared region. Values of the wavelength for radiations of infrared region are higher than the wavelength of the radiations in the visible and ultraviolet region, but the value of energy is less. Unlike UV spectroscopy, in which the spectrum comprises of relatively few peaks, the IR spectroscopy provides a spectrum containing a large number of absorption bands, which provides ample information about the structure of an organic compound. It basically gives information about the various functional groups present in the compound. Infrared spectrum is an important record which gives sufficient information about the structure of a compound. When an infrared light is passed through a sample of an organic compound, some of the frequencies are absorbed while other frequencies are transmitted through sample without being absorbed. If we plot the percentage absorbance or percentage transmittance against frequency, the result is an infrared spectrum. Different bonds, for example, C single bond C, C double bond C, C triple bond C, C double bond O, OH, NH, etc., have different vibrational frequencies, and we can detect the presence of these bonds in an organic molecule by identifying their characteristic frequencies as absorption bands in the infrared spectrum. The absorption of infrared radiations causes the various bends in a molecule to stretch and bend with respect to one another. The absorption of infrared radiations causes an excitation of molecule from a lower to the higher vibrational level. We know that each vibrational level is associated with a number of closely spaced rotational levels. Clearly, the infrared spectra is considered as vibrational rotational spectra. All the bonds in a molecule are not capable of absorbing infrared energy, but only those bonds which are accompanied by a change in dipole moment will absorb in the infrared region. Such vibrational transitions which are accompanied by a change in the dipole moment of the molecule are called infrared active transitions. Thus, these are responsible for absorption of energy in the infrared region. On the other hand, the vibrational transitions, which are not accompanied by a change in dipole moment of the molecule, are not directly observed, and these are infrared inactive. The most important region is 2.5 micron to 15 micron, in which molecular vibrations can be detected and measured in an infrared spectrum. So here you can see a figure showing infrared region. You can see here there are three divisions. One region is a near infrared region, then next is infrared region, and then comes far infrared region. At the top, wavelength is shown, and at the bottom, wave number is shown. The absorption of infrared radiations can be expressed either in terms of wavelength or in wave number. The ordinary infrared region extends from 2.5 micron to 15 micron. The region from 0.8 micron to 2.5 micron is called near infrared, and the region from 15 micron to 200 micron is called far infrared region. In terms of wave number also, you can see the infrared region covers 4000 centimeter inverse to 667 centimeter inverse. The near infrared region covers 12,500 centimeter inverse to 4000 centimeter inverse, and the far infrared region covers 667 centimeter inverse to 50 centimeter inverse. So just have a look. Mostly infrared spectra of organic compounds are plotted as percentage transmittance against wave number. The relationship between wavelength and wave number is as follows. Wave number is equal to 1 upon wavelength in centimeters. Mu represents microns. 1 mu is equal to 10 to the power minus 4 centimeters. So wave number in centimeter inverse is equal to 10,000 upon wavelength in microns. Infrared spectroscopy is a very reliable technique for disclosing the identity of a compound or to determine the structure of a new compound. In determining the structure of a new compound, it is useful to predict the presence of certain functional groups which absorb at definite frequencies. For example, carbonyl group of ketones gives a strong bend at 1710 centimeter inverse. Esters show two strong bends between 1380 to 1050 centimeter inverse. Phenols absorb near 1200 centimeter inverse. Hydroxyl group in a compound absorbs at 3600 to 3200 centimeter inverse. We'll be studying this in detail further later. And the shift in the absorption position helps in predicting the factors which cause this shift. Some of the factors are inductive effect, conjugation, hydrogen bonding, etc. So thank you so much. Today we just studied the introduction part of infrared spectroscopy.